Hello everyone, I hope you're all doing very well. I'm going to present today the lubrication systems of the marine diesel engines. And here is a summary of what we are going to be discussing about. Um, First on your right here you can see um, two pictures. One is a very large Wärtsilä engine, the largest in the world. And here is the Emma Maersk, which is actually using this engine as our main engine. So, back on the topics today. We'll talk about the role of lube oil first, and then lube oil bunkering. Then you may have a question why so much lube oil is stored on board the ships. And also, what are the factors that are going to impact the lube oil consumption? We'll go through a quick review of the lube oil properties so we understand why it's important to monitor in particular and what the action of the lube oil is on the engines. Then we'll go to a description of the components of a lubrication oil system. We'll talk about the various types of oil systems, then zoom into the different parts like the main lubrication system, lube oil treatment, go to the engine cylinder lubrication system, and then to the turbocharger lubrication system. I'll be then describing the importance of monitoring the lube oil quality, brief overview of the onboard testing of oil, lube oil, and then what another type of testing, which is more an oil analysis, is bringing to us. This analysis is being done onshore. So what are the lubrication oil functions? The lube oil is provided to the moving parts of the engine, as you all know. Its main roles are to reduce friction, leading to engine component wear, and also minimize the corrosion by removing oxidation particles. It had also a very important effect, which is cooling the engines by removing the heat. It also helps protect engine components against the harmful deposits, and it dampens mechanical shock in gears. It also forms a seal on the walls of the cylinder. Now, bunkering is not just fuel. It is also oil that is considered as bunker. So I'm showing here a few pictures. The lube oil can be delivered in like oil drums or bulkier. You can see that barge here. This barge is specialized in providing various type of lube oil. Each hose is connected to a specific tank with a specific lube oil type. You've got here a view of a typical barge delivering oil, and here oil drums being stored near the engine room on the ship. Where is this oil stored? Here's a very simple tank diagram, and you can see the various tanks with colors, like fuel oil is yellow, ballast is green, and lube oil is orange here. So you have dedicated tanks for lube oil. If you look at the state of Maine, our training ship, looking at the GA drawings, capacity plan, you can see where the lube oil is stored. So you see the stern here, and I'm going to zoom, and you'll see there is a cofferdam here, engine room, and you have the main engine lube oil storage tank located here. Now looking at another view of that capacity plan, you can see again storage tank here. And here are the tables that are also included in the capacity plan. So you see we've got heavy oil, fuel, all the tanks, capacity, their designation, frames where they are located. It's also providing the density of the fuel, of the liquid being stored, capacity. So capacities are given 100% full and 98% full. Obviously, the capacities are never 100% full, so 98% full is closer to what practically full tank should be, although in various companies they prefer considering 90 or 95% of the capacity. So the rest of it, are for stability calculation, mostly. You see center of gravity, moment. And as far as we are concerned, looking at the lube oil more specifically, you have that storage tank here, which has a capacity of 401 cubic feet when full, 100%. You've got another tank here, which is a settling tank, just like for the fuel oil. It's supposed to let the fuel or the lube oil settle to separate any possible impurities that could have occurred. And then you have another storage tank here, which is much bigger. And you have here a settling tank, which is also much bigger. So when you look at the total lube oil capacity of the state of Maine, we got about at 85% about. If we consider 85% as what should normally be applied, you got about 25,000 gallons of capacity. So you would wonder why so much oil is stored, and because it is consumed and lost progressively. It's just like cars, if you get a certain oil consumption, you need to top it off from time to time, especially on older vehicles. Here I put the example of a Wärtsilä 4-stroke engine, the 18V32. It's a 9,000 kilowatt output engine, pretty big. You can see here in this picture it's installed in a power plant. Here is a cut of the engine in question. And well, to be able to run these engines need a lube oil volume of 12 cubic meters, including 5 cubic meters in the sump here. And the oil tank has to be kept 80% full. There is an alarm when it reaches 60%. Just to give you an idea of how important the flow of oil is, and through such an engine, you must have a continuous flow of 164 cubic meter per hour, which is considerable. Now that when you look at the specification sheet of this engine, you see that the consumption of the lube oil for this engine is 0.35 grams per kilowatt hour. It may not be very looking important, but it is not negligible, and that represents about 19 gallons of lube oil consumed per 24 hours. And that's pretty good compared to what that used to be in the older large trunk piston engines, two-stroke. You could have 1 to 1.5 grams per kilowatt hour of oil consumption. So it is significantly lower than that due to technology improvements as well, and to the fact that we are dealing with a four-stroke engine. What are the factors impacting lube oil consumption? First, there is the engine design itself. You have different ways of designing an engine, and it boils down a lot to the number of piston rings and their design, the scrapers, the condition of the cylinder liner. A lot of the oil is actually burnt in the cylinder, as you understand. Also, another factor here is the quality of the oil. Oil can be more or less adapted or more or less good quality, and it could be also affected by storage condition, contain water and impurities like rust inside, all sorts of things that would make the oil not behave as it should be. Another reason is the fuel quality. You can have poor fuel quality due to supply or storage, and that's also that time. It's if you have oil contaminated by fuel or residues from the fuel, it's often a reason to change the oil. So obviously this is adding to the overall lube oil consumption. Then you have the operating conditions, just like a car or any engine. It depends a lot on a engine load. If you start and stop often, the maintenance, like injectors are not properly maintained, so you may have a fuel leakage from the injectors, so it creates debris or residual fuel that mixes with oil and contaminates the oil, etc. And then you have also the losses in the system itself. You saw with Professor Wallace's presentation about the purifiers and centrifuge machines. Well, these machines, if not properly operated and maintained, you can have losses. You can have sludge that are eliminated too often, for example, and wrong adjustment of some parameters to optimize the operation of the purifier. On filters, you can have backflush that are not properly working, and also you can have a number of leaks that are happening on the vessel. And this is estimated to 0.1 to 0.2 grams per kilowatt hour generally, which is opposed to the 0.35 gram per kilowatt hour that the engine itself is supposed to consume. Be aware that generally, except any accident like oil contamination, engine lube oil is generally changed 1 to 2 times a year. Now, a quick review of the main oil properties. One of the most important properties is viscosity. The viscosity of an oil is its tendency to resist flow. It's closely related to reducing friction in contacts. Also, the higher the temperature of the oil, and the lower the viscosity will be. And there is a very important parameter that is the viscosity index, or VI, which is based on the slope of the temperature viscosity curve. Here is the diagram: viscosity and temperature. Viscosity increasing, temperature increasing. So a higher VI, or viscosity index, is represented by that curve. The viscosity index scale was originally set up by the Society of Automotive Engineers, SAE, and you certainly all heard about the oil grades like SAE 10W40 for cars, vehicles. But here are the viscosity index classification. Under 35, it's considered to be low viscosity. From 35 to 80, medium viscosity. From 80 to 100, high viscosity, and above 110, very high viscosity. So now there is single grade engine oil, which is defined by SAE J300 definition, and there are 11 viscosity grades, which are 0W, 5W, 10W, 15W, etc., up to 60. At one point it drops a W. So as I was saying, when you deal with SAE 10W40, it is a lube oil that acts like an SAE 10 at cold temperature, and 10W stands for winter, and like an SAE, and behaves like an SAE 40 at the temperature of 100 degrees C, or 210 Fahrenheit. Here is something that would help you understand better. On this diagram here, you see that the x-axis is temperature, and the y-axis is the viscosity here. So you've got two slopes here. One is the oil being tested at low temperature, cold temperatures, and the other one is at high temperatures. And so the line defining the SAE 10W40 is located here. And they are viscosity grading systems that are used by the industry and by everyone. You have on a scale here, which is in centistoke, CST. CST is a unit of measurement of the kinematic viscosity, centistoke. There are others, but this one is much more widely used, industry standard. And centistoke is a derived centimeter gram second unit of kinematic viscosity. Well, it's actually expressed in millimeters per second. Different type of oils that you can see here: 5W, 10W, 15W, 20, 30, 40, 50, 60 for a crankcase. Here you've got different oil qualities, different viscosities for the gear. So that was viscosity. Now there are another extremely important parameter, the flash point. And the flash point of an oil is the temperature at which that oil can be ignited when a flame or a spark is present. The flash points are typically above 300 Fahrenheit. And under normal condition, you never reach 300 Fahrenheit, but you can have cases where maybe the lubrication quality and the friction together lead to high local temperatures. It could be in the crankcase, for example. If you have a lubrication issue, you could have vapors that could ignite, and this is a frequent type of accident on board vessels, that you have mist igniting, and you have safety valves on the crankcase, but well, this is always a dangerous situation, so it needs to be monitored, and it's actually monitored by instrumentation on the crankcase. Another important parameter, the pour point. It refers to the minimum temperature at which a lubricant continues to flow, and below that pour point, the oil ceases to flow freely. It's become like jelly. And the last important parameter here, the TBN, called total base number. This is an important measure of alkaline concentration in a lubricant. And this alkalinity is important. It's designed to combat the buildup of acids in a lubricant as it breaks down. So this is a parameter that is frequently tracked. Again, I'm not trying to here to do a lubrication or lubricant course. There's much more to talk about. It's just provided so we have a better understanding of what's following and how the lube oil actually operates in equipment and engines in particular, in our case here. What are the components of a lubricating oil system? There are two main divisions. One is inside the engine, and the other one is outside the engine. I have put here a car engine drawing, 3D drawing, and this is from an Audi V6 engine, but they all work about the same in terms of oil distribution. We'll see what the differences are later as we go. And this inside the engine, it's mostly composed of a lot of passages and openings, little pipes that are conducting the oil to the lubrication spots. In green you have the clean oil, and in yellow you've got the dirty oil. On every car and every vehicle you have a filter. That's a filter, so the dirty oil goes into the filter and gets out of the filter clean and ready to be used again. So it goes to different points. It's going to the crankshaft, bearings, main bearings of the engine. It's going to the camshafts here. So there are distribution points at several levels of the camshaft, and it's also lubricating chains and gears. It's also lubricating the crankshaft, and well, when it has finished its cycle here, it falls into the sump in the bottom of the engine and is pumped back using a pump, an oil pump, which is a PD pump, positive displacement pump. And so that oil is sucked again and sent back to the filter where the cycle continues over and over. Another view of the internal oil flow of engines. Here is another car engines for cylinder, apparently. Same thing here. The sump, and it circulates the gear, the oil pump. Let's look at the lubrication oil systems of a main engine, a marine main engine, diesel engine. You generally have at least two separate lubricating systems on large, slow or medium speed main engines. You got the main lubrication oil system here. The second system you have, and this is quite frequent, is having a separate cylinder lubricating system. Here's the cylinder, and quite frequently you have a separate system, which is the turbocharger oil system. Another view, very similar to what I showed you, with different angle. So that is the main lubrication system. That is a cylinder lubrication system. And that is the turbocharger lubrication system. Looking at the main lubrication system, you will see various functions and components here. First, you have the lube oil setting tank. We earlier saw where this, in a ship, this tank is located. So that settling tank sends clean oil to the main engine sump here. So that oil must be brought, it's fresh oil, clean oil. The level or the volume in the sump must be maintained at certain level, so this level is maintained. Here you've got the purification, the filtering system and the pressurizing system. We'll get back on that. And here you've got the purification system. You recognize here lube oil purifier. So we're looking now more specifically at the main lubrication system, the treatment and the lube oil filtration system. So we're talking about that part and this part, which is a purifying system. Here's a very simple diagram showing the main lubrication system and the lube oil treatment. Lube oil treatment on that side and the full flow filtering system on this side. So here is a oil sump, and this is being used to collect the oil after it has been used to lubricate all the engine parts here, so it falls here. here you got a part of the flow. It's a small part, 1% of the full flow, but it's continuously running in closed loop like this from the oil sump back to the oil sump, and it goes through a PD pump here. Then it goes to a heat exchanger. You would wonder why it needs to be heated, why it's so hot here, but it may not be at the right temperature, and it's very important to ensure purification efficiency here, that the lube oil is maintained around 95 degrees C. So that's why the heater is here for that job. So then it goes to the separator, and again you saw on a previous lecture how a separator works. And this is configured as a purifier. So obviously it produces sludge during the purification process that goes to a sludge tank, and then it goes back to the oil sump. Again, it's 1% of the full flow, roughly. Now the filtration system by itself, or the full flow filtration here. Same thing, it starts in an oil sump, there's a pump, then it goes to a cooler and to a full flow filter system, and this is lubricating the engine. This is the where the oil, clean oil, is entering the engine. So that's cooler here is not a heater, it's a cooler really. It maintains the oil temperature within a certain range, and you will understand that if it's considering that it's a closed loop, little by little and very quickly actually, the lube oil will, at the contact of the various friction parts in the diesel engine and combustion, etc., the lube oil temperature would raise in temperature. If there was no cooler, it would keep on raising, it would keep on getting higher and higher, and to the point where the oil will be, temperature will be above its working range. And so viscosity will be too low. The full flow filter, that one is extremely important. It's the last line of defense, and it's the equivalent of the filter you see on your car engines. It eliminates abrasive particles. Talking about filtration would justify a class by itself. So here we are going to give some basics. The filters operate with a filter media made of wire mesh, at the difference of other filters, the type of filter we are going to talk about, which is this type of filter installed on large engines for very large oil flows. They are not made of paper or cellulose, they are made of a wire mesh. So when the pressure drop over the filter indicates the presence of a sludge layer, the filter elements are cleaned by back flushing. And this is generally done automatically or sometimes manually. But based on the pressure difference, when it's clogged, you've got obviously a big pressure difference here. So the main parameter to define a filter is the mesh size, and it's the size of the openings in the filter. Like here, some examples of filter close made of wire. So different patterns. You have some example of the shape of particles. Some of them are perfectly round, some of them have this shape, some of them are like that, like a little wire. Anyway, it's supposed to be capable of catching all those particles, and they are filtered from 6 to 40 microns size, and the mentioning here, a grain of table salt is about 100 microns, so you see how small that is. How does this full flow lube oil filter works? So you have first you've got here in the bottom right, you've got disc shown here. They are like disc with all around filter cloth, just like we saw here. Those filters here are stacked. They are different disc stacked on each other, and they are stacked in this chamber here on top of each other, a little bit like in separators that you saw centrifuge machines. And they also stacked here in this other chamber, which is called the diversion chamber. You have here an hydraulic motor. It uses some of the lube oil here to rotate periodically. That's where the unfiltered oil enter the filter, and that's where they come out of the filter. Other element here, where you can see those discs, is the diversion chamber, where all the impurities, the sludge, etc., accumulate. Here is a valve connected to that chamber, so it's either manual or automatic, but when you open it, it flushes out the solids and impurities that have been accumulating here. Let's go to the next slide. Here the operating principle. You have generally this type of filter work into two phases. So this is a phase one. You've got the unfiltered lube oil coming inside, and it goes here and gets outside filtered. But after a while, the filter becomes, impurities start accumulating on the disc that and meshes close, filtering close we talked about earlier. So what happened then, there is a rotation of the hydraulic motor, which is here, and you can see here is how the hydraulic motor turns. There's a little pipe connecting that chamber to the motor. It makes it rotating. It eliminates loosen some of the debris. Then what you do is you backflush the filter. So that time, while we keep on getting filtered oil out of the chamber, but at the same time, it goes in the opposite flow here towards the center of the stack. You see here it was doing that, it was coming out, but here some of it goes out, but some of it gets in here, and then flushes all the impurities, which are shown in brown, dark brown, and accumulate them into that chamber. So once in a while, that debris drain valve should be open to flush that, and then we're back to phase one. Now, engine cylinder lubrication. We've seen that there are three different systems. You've got the main oil lubrication system, and here the cylinder lubrication system. We just talked about that one. Now we are going to talk about this one. Discussing about large engines mostly, but regarding engine cylinder lubrication, smaller engines have the main lubrication system taking care as well of lubricating the cylinder. Smaller engines are like car engines or genset, generator engines, like Caterpillar engines and so on, or Cummins engines. And the oil is like projected here and is trapped here in the piston rings, and then does the lubrication job. Now for large bore diesel engines, it's a separate system. And cylinder lubrication is extremely important in order to lubricate the piston rings, also reduce friction between the rings and the liner, and it also provides a seal between the rings and the liner. The rings provide a seal with the liner, but with oil it's even more effective. And also it helps reducing the wear due to corrosion by neutralizing the acidity of the products of combustion. It's a very aggressive environment. Just a quick idea how that cylinder lubrication works. Here's the cylinder liner, and around the liner you've got lubricating quills all around, with little pipes injecting the oil. You can see it on that picture, the distribution here, and you've got those lubricating quills all around the cylinder. And so those multiple quills, they work in a group to spray the lube oil on the liner surface. So every time there is an upward stroke movement of the piston, which is here, then you've got oil injection. Another view here of the different components. You have an elevated tank, shown very little, but it's bigger than that. Filter, and here you've got a system, lube oil distribution control system, which is deciding where to send the oil to the quills. Generally they don't act all together, but some of them work during one stroke, and the second stroke the others, etc., etc. So it's important to know that the cylinder oil dosage is proportional to the engine load, which is the cylinder fuel supply. There is also an important aspect, which is that the oil dosage here must be proportional to the sulfur content of the fuel. Remember, it is protecting the it's neutralizing the acidity of the product of combustion, otherwise there would be a quick oxidation. If you are using a low sulfur fuel, well, you generally need to use a different oil. I recommend you watch that very, very good animation from a company named Total Lube Marine, and I put the link here. You can cut and paste the link from the PowerPoint version of that presentation. It's very well done. Now the third system, turbochargers, and it's a high-speed rotating machinery. It goes from 8,000 RPM to 250,000 RPM, depending on what type of turbos you're using. And so you would imagine that the bearings need to be very well lubricated here. All sorts of challenges for those bearings. So, a quick description of a turbo. That is showing what a big turbo from ABB looks like. And you've got two parts here. You've got the air side of the turbine, which is called the blower, and the other side is the exhaust gases. So you certainly remember the principle here. The exhaust gases enter here, drive the gas turbine, then it goes to the exhaust, sometimes used to in an auxiliary boiler to produce hot water or different services. But while doing that, turbine is driving the blower, here the compressor. So that compressor is then injecting air into the cylinders at a higher pressure. Here is a filter. Air filter. So the turbocharger bearing lubricating system can be completely separate from the main engine lubrication system, or it can be fed through the main engine lubricating system, which is a more frequent case, depending on the design. Two main different designs here, and both are using independent and dedicated filtration system for oil. You got what it's called the outboard bearing design, and you got the inboard bearing design. So all those systems need an elevated tank. Anyway, that elevated tank is there to ensure a certain pressure for the case of the standalone system, and it must be able to provide a 10-minute here or 15-minute supply in case, well, not when you shut down your engine, and if it's the oil is provided by the main engine, as it's the case for that inboard bearing system, then the oil pressure is likely to fluctuate or go down, or if there is a breakdown, it would go down. So they are very sensitive pieces of equipment. So in order to ensure lubrication, while their speed is slowing down, you in that elevated tank you have a 10-15 minute supply of oil for continuous lubrication and cooling. So head tanks, gravity tanks. So back on the design, the outboard bearing design has its own lube oil system, and here is a view of that, what it looks like. It's very recognizable. When you look at the turbo, you generally see a sight glass on the side, on both sides, on the air side and on the gas side. You see the sight glass here, and there is a casing here. The shaft of the turbo is here. Your casing with an oil sump, and so that oil is lubricating bearings, which are here. Now the other system is this one. You see there are no bearings, no ball bearings, but you have sleeve type bearings or journals, which are different type of bearings, and you remember certainly what they are. In this case, you got the lube oil from the engine, main engine system, getting straight on those bearings. Now, there are advantages and inconveniences with the two systems. This one, for example, if you need to change the bearings, you don't have to. You just have to remove the ends and change the bearings. This one, if you want to change those bearings, you have to remove the whole, disassemble the whole turbo and separate that in order to remove the bearings. This system is probably a little bit more common, especially on large turbochargers. They must They must handle high loads, those bearings. They must withstand challenging and extreme conditions like rolling, pitching, yawing of the ships. It moves constantly during storms, mostly high seas, and those turbos, by the way, are designed to be capable of sustaining angles of about 15 degrees without causing any disruption of the operation. But they also have those bearings to sustain high temperature peaks and hot shutdowns. They must not react with lube oil, and they must have a high thrust loading. Here's an example of a sleeve journal type bearing, like you would see here. Now we are getting to the end of this presentation, but before we conclude, I want to stress the importance of monitoring the engine lube quality. We know how important lubrication is. We saw that earlier. By the way, to do that, it's to monitor the deterioration of oil over time and to check for contamination with other oil, water, and bacterial attack. There may be bacterial attack if there is humidity in it. And to avoid damage to the lubricating part of the machinery. And to identify any leak or source of contamination of oil. It could be fuel, it could be water, it could be a lot of different things, but mostly that. And also to understand the performance of the lube oil. It may change over time, and but at a certain point you would understand how it performs. It gives you a snapshot of the condition of the oil, certain parameters. Here are some alert limits from an Alfa Laval white paper I found. You have an alert limit for viscosity at 40 degrees, so you measure the viscosity at 40 degrees, which is a maximum of 140, and then you condemn the oil if you get to 150. Flash point, we saw that we don't reach normally 300. The alert limit is at 200, so it gives some safety margin before we reach the maximum where we know the oil may inflame with a spark. Water content, this is extremely concerning. When we see the water content getting elevated, there may be a leak from the jacket cooling system, or an accidental water entry in some external part of the treatment system. So the onboard testing using that kit here will help provide that water content indication, doing a water content test with this electronic equipment. You can also do you will also do a pH test using a pH paper that would tell you what the reserve of alkalinity of the oil sample is. You can use this equipment, there are others, but to do a viscosity test, and if you have a low viscosity, it may be contamination with oil, fuel, or sludge. Spot test, that is to compare on a blotter paper. You compare the appearance of the oil clean with the oil that you are testing. Last very common one is a flash point test, as I mentioned earlier, quite important. This is done by various type of equipment. This one is an electronic testing equipment, easy to use. Now the very important other aspect. You've got the onboard oil analysis, but you also have another one which is very widely used, is analysis done by the Shore Labs, and there are multiple companies doing that. And it's a very, very good tool, part of the condition monitoring and predictive maintenance of engines. You save a lot of money doing that, and you also can predict what you need to do at this point. If you need to overhaul an engine, and I personally have done that multiple times, planning an engine overhaul based on various parameters, but also the condition of the engine oil or equipment oil. It's a great dashboard. So we will see, I will explain a little bit later what sort of information we get from that. But you see, we can make maintenance decisions based on these results. We can avoid oil mix-up. Sometimes these analysis tell you, you've got two sorts of oil that are mixed together and it shouldn't have been done. It's a mistake. And you see a lot of pieces of metal. It could be zinc, it could be bronze. That tells you that a piece of the equipment is wearing out. So it's what it basically shows. See your water, change filter, change oil, tear down, and could be machinery wear, lubricant degradation, lubricant contamination, all this will be shown on the analysis results. So you periodically, once a month generally, have someone picking up a sample and labeling it properly to avoid having the result of another piece of equipment and make mistakes in terms of decision making. And so this is extremely useful, and even now it has become so widely used that it is a requirement from many classification companies to be able to show your tracking the evolution of your lubrication oil. That is what you get. We worked a lot with that lab, ALS tribology. Tribology is a science of movement and wear. This is very comprehensive. You see, when you've got all those parameters here, so every month you send a sample. This is for a diesel engine. It could be diesel engine number 1. And so here it's tracking the result months after months. You don't have to spend much time. You see that it's all good. Your parameters are within the range. And then all of a sudden you've got a stop or a caution mark, and it means that something is wrong somewhere. So you look at your results here, and you see, oh, I've got too much water, or I've got here too much sodium or too much potassium. Sodium, for example, would indicate you, especially if you have water with it, it may be an entrance of seawater here, as an example. And you've got some other elements like iron. Here, metals. Metals are very important to show if you've got wear in your end. Iron may be because you have some parts getting oxidated. Know more about specific wear. You can correlate that with engine parts. Get with a manufacturer and ask them what sort of alloy they have in, or what specific parts have such or such type of alloy, and get closer to understanding where you get wear starting in your equipment. So you also have the viscosity indicated here. the fuel content in your oil. Very, very handy. Thank you. That concludes our lecture for today. Please send me or Professor Wallace any question you may have, and I hope you are all doing really well right now. We miss you.